My name is Tim, and my project was on the CRIS 2.0 disaster evacuation model graph generation. So CRIS 2.0 is a project funded by the NSF that deals with evaluation of infrastructure. And to be specific, CRIS would stand for Critical Resilient Interdependent Infrastructure Systems and Processes. So some background on my project is related somewhat to Anna's project. The concept that disasters and hurricanes and other disasters can cause damage to a region, and it's important to understand how people behave, what kind of infrastructure we have to support these kind of evacuations, and in terms of my contribution to create a model that would assist in the visualization and understanding of these kinds of disasters. So my project dealt with the generation of graphs to represent neighborhoods and to simulate how people would evacuate. So some concepts that we need to introduce are this directed graph, which is based on Kleinberg small world networks. And so we can view nodes as being families or homes, and we can view edges as influences that families have on each other. So in a real world context, this would be something like one family chooses to evacuate, and then a neighbor would see this family evacuate and would therefore choose to evacuate as well. The edges within this graph consist of short-range edges, which simulate neighbors. So people within a certain geographic distance threshold of one another would be influenced by their neighbors, and long-range edges, which represent more geographically distant friends of the families who would nonetheless still have influence. And to simulate clustering in these networks, we utilize a distance-based weight system, which is used for the long-range edge selection. So my goal in this project was to implement multi-threading and parallelism in the project to accelerate the runtime of this graph generation. Inputs included the node data, such as the latitude and longitude coordinates, the number of threads desired for the run, the distance thresholds, which determine short and long-range edges, and random number generation to assist in multiple runs of the code. And so the structure of our code was a nested for loop to assign every node its neighbors, and my parallelism was intended to accelerate this process. So some results of the runtime indicate that the use of more threadeds resulted in a moderate increase in time. As more nodes are added to the graph, the runtime increases exponentially, and we expect a greater benefit when this is run on more massive scale graphs. So some future work that could be done includes further testing on different machines, a distributed system which could potentially parallelize the project even more by assigning partitions of the nodes to multiple machines, and implementation of faster searching methods, such as binary search in the long-range edge selection process. Thank you.